Uh, Good morning, everyone. It's like 3 o'clock in the morning here. I just went to bed early, wake up, so I decided I'll make you another lecture. First of all, happy Palm Sunday for those of you who are Catholic or Christians. I am. So happy Palm Sunday to all of us. And so today I'm going to continue with the Taylor polynomials and so forth. I had a couple of questions about people not being able to do some problems. So let's work on them and see what we can do. So let's say we have f of x that is continuous and fn of x exists, okay, on some intervals. So this is the nth derivative exists. Then the Taylor polynomial about x equal a is given by Pn of x is k equals 0 to n f of k of a over n factorial times minus x to the power a to power n. So this is a Taylor polynomial. For example, last time we had f of x equal e to the x, and let's do it about x equals 0. So we said f prime of x is e to the x, f second of x is e to the x, and then we know the nth derivative of x is equal to e to the x. So f of 0 equal f prime of 0 equal to fn of 0 equal e to the 0 is 1. So this one here, so Pn of x is k equals 0 to n. Now fk of a, this is fk of 0. So fk of 0 is 1 over, sorry, this is n factorial, guys. This is k factorial over k factorial times x to the k. So that is k equals 0 to n xk over k factorial. Okay, so that is the Taylor polynomial of f of x equal e to the x centered at x equal to 0. So we can do it at any point x equal a and so forth. So if you want to do this, f of x equal e to the x at x equal 2, say, then you know f of prime is e to the x, and f of prime of 2 is going to be e to the 2. So forth, then fk of 2 is going to be e to the 2. And so the polynomial here, Pn of x, would look like this. K equals 0 to n fk of 2 over k factorial x minus 2 to power k. So this is what would that be. And if you put it down, this is k equals 0 to n fk to power 2 is e to the 2 over a factorial k factorial x minus 2 to power k. Okay? You see how easy it is? Alright? So it's really not that hard. It's just simple calculations and so forth you follow through with. Alright, so go ahead and take a look at it. Let me have a sip of my tea. Alright? So let's now take a different function, if you like. If I take, for example, f of x equal x squared plus 2x plus 3. Let's make it x cubed. And I wanna find Pn of x around 0. Okay? So that mean a is 0. Okay? So you start with f of 0. You need to calculate these. So f of 0, this is f of 0, and you put it here, you're gonna get 3. And then you're gonna get f prime of x. That will be 3x squared plus 2. F prime of 2, no, I'm doing it at a equals 0, sorry. That will be 2. F second of x is 6x. F second of 0 is 0. And f third of x is 6. And f third of 0 is 6. So now let's write the formula here. So the formula is going to be Pn of x equal to k equals 0. Now if you look at the fourth derivative, so the rest are all equal 0, if you see. Because the fourth derivative is going to be 0. So you have to stop at 3. So it's going to be k equals 0 to 3. You see that? And it's going to be f of 3 of 0 over k factorial times xk. So if you write this, this is going to be f of 0 plus f prime of 0 over 1 factorial times x plus f second of 0 over 2 factorial times x squared times f third of 0 over 3 factorial times x cubed. And then you can put these values in here. So this is going to be f of 0, we said, is what? Is 3 plus f prime of 0. F prime of 0 is 2, 2x. F second of 0 is 0. F third of 0 is, what is it? F third of 0 over 3 factorial, that is 6 over 3 factorial x cubed. And take a look at that. That is this equation again. So this one is nothing but this one, guys. Okay? Because that's a polynomial. Alright? Because we did it at 0. So if you do it at x equal 1, you're not going to get the same answer. Okay? Because you are shifting your parabola to the right by 1 unit. Alright? So this is the polynomial, Taylor polynomial. Now, let's take a look at Taylor's theorem. This is a section now. This is section 10.9. Okay? All right, it says, suppose f of x is continuous on AB and fn of x exists, every one of them, on a closed interval AB. Okay? Then the polynomial said, then you have f of b, then f of b is going to be f of a plus f prime of a over 1 factorial x. X sorry, it's going to be b minus a plus f second of a over 2 factorial b minus a squared plus a plus, and then for some c, and then it's gonna be a plus f. Oh, so this one, let me write it down, is gonna be f n of a over n factorial b minus a to power n, and then this one fn of a over n plus 1 factorial times, oh, this is gonna be c here, b minus a to power n plus 1 for some c in AB. So this is what Taylor polynomials say. All right, so this is going to be for some c in AB, and if we can show, so this is going to be the Rn. Okay, so take a look at the formula again. All right, so if we replace x with b, so basically we are looking at the interval ax, then we have f of x, f of a equal to, this is f of x, sorry, because we're replacing b by x. So it's going to be f of x into f of a plus f prime of a over 1 factorial, that's going to be x minus a plus fn of a over n factorial x minus a to power n plus fn plus 1 of a over n plus 1 factorial x minus a to power n plus 1. Actually, this is going to be, sorry, going to be c. Okay? So this term is c. So this term we're going to call the remainder. All right. So we're going to call this one is Rn of x. And so f of x is Pn of x plus Rn of x. Okay? So that is k equals 0 to n f of k of a over k factorial x minus a to power k plus Rn of x, where Rn of x equal to fn plus 1 c over n plus 1 factorial times x minus a to power n plus 1. Okay? So this is basically what happened here. So if we can show that limit goes to 0 as n goes to infinity, then we are done. So basically, so if Rn converge for all x, that means this Rn means that the limit exists for all x, and it's 0, has to be 0. I mean, then this will converge for all x, okay, on that interval. So this is what we have so far. So this is the Taylor polynomial. All right. So let's take a look at, so let's consider, this is an example now. about x equals 0. That means a is 0. Okay, so let's calculate. So basically f of x is k equals 0 to n fk of 0 over k factorial xk plus, this is e to the c over n plus 1 factorial x to the power n plus 1. Okay? All right. So what is the c? So this is your Rn of x. All right? So remember, x is fixed. So you fix x between minus infinity and infinity. So let's say x is minus infinity to infinity. All right? And so this is, we have already done this before. Fk of 0 is 1 over k factorial xk plus Rn of x. Okay? So we need to make sure that this limit goes to 0 for any fixed. So let's take a look at, so basically, so if x is negative, if x is less than 0, then c is gonna be less than 0, then e to the c is less than 1. Okay? Alright? And if x is positive, then e to the c is basically gonna be whatever it is. So c, e to the c is gonna be less than e to the x, because c is between, because remember c is between 0 and x. Okay? So whatever that number is. Alright, so if we look at the limit, regardless of e to the c, let's take the absolute value over n plus 1 factorial, that is going to go to 0. Alright? Because the n factorial will kill that limit. Remember, x is fixed. This is for any fixed x. So that one will kill it off. And that is going to be to 0. And this tells me, hence, the Taylor series of e to the x converges for all x. Okay? So this it converges for all x and so forth. And we can do other examples. So anytime you have n factorial, remember x is some number fixed, 2, 3, whatever you want it. Still, even 100, 1,000, a million is not going to make any difference, because n plus you keep taking the so you take the limit. If x is 2, this infinity over infinity, and then use L'Hopital's rule infinitely many times as you need, and you will see this will win, and then you will get 0. All right. So now let me ask you to work on, for a second, just think about f of x equal sine x, and let's take a equals 0. Go ahead and set it up for a second. Okay, so we need to write the Taylor's polynomial. So we know f of 0 is 0, f prime of x is cosine x f of prime of 0 is 1, f second of x is minus sine x, and f second of 0 is 0, f third of x is the derivative of minus of sinus, so we have cosine x, f third of 0 is 1, and so forth. So why don't you continue with them for a second, go up to the fifth derivative, and then I will join you. Oh, sorry guys, I messed up. This is minus here, so that's going to be minus 1. Okay? As you see, so we're going to have f of 2L is, if you have f of 2L is going to be minus 1 to the L sine x, and f of 2L plus 1 is going to be minus 1 to the L cosine x. Okay? And the funny part is, these f of 2L at 0, they'll all give you 0. Except this one. So this one, f of 2L plus 1 at 0 is minus 1 to the L times 1, that is minus 1 to the L. And if you write it down, now you will see f of x equal to x minus x cubed of 3 factorial, and do the plus x5 over 5 factorial, and then you will see that. You see, what happened is f of 0 is 0, okay? So there's no contribution from this one. And then f of prime is 1, so you'll get this x. F second is 0, f third is minus, you will get that. Then for L equal to 4, if you put L equal to 4 here, you will get f fifth, that is positive, all right? Put L equal to 5. So put L equal to 3, we said here, L equal to 2, L equal to 3 will be 6, will be 7. 7 will be minus. So you see the next term is minus x7 over 7 factorial. You'll see that. Take n equal to 4. If n equal to 4, L equal to 4, you will get 2L, that's 8 plus 9, and that will be positive. Plus x9 over 9 factorial, you see? Alright, so we would like to have a formula. Can you create a formula for that? So what do you think? Go ahead and create me a general formula. So this one is going to be k equals 0 to n minus 1 to the k, and it's going to be x to the 2k plus 1 over 2k plus 1 factorial plus Rn of x. Okay? If you add this one, if k equals 0, you will get the first one. K equal to 1, you will see, you will get that one. And this will be minus. Alright? K equal to 2, you will get that one. K equal 3, K equal 4, and then you go all the way to n plus Rn of x. Okay, so what is Rn of x? Can you write it down for me now? So go ahead, write me Rn of x. What is it? Rn of x. It's going to be the n plus 1. It's going to be minus 1 to the n plus 1, x to the 2n plus 1 over 2 times n plus 1 factorial. Okay? And that's going to be minus 1 to the n, x to the 2n plus 3 over 2n plus 3 factorial. And then if you take the lim of that, this is going to be, let's take the absolute value, or actually it doesn't really matter. Minus 1 to the n, x to the n plus 3 over 2n plus 3 factorial. Remember, x is any number fixed, and that's going to be 0. So by Taylor's theorem, we say the Taylor series of sine x converges for all x. So basically now what we can do is, so we can write sine x as, now we're going to switch n equals 0 to infinity. Once we show the limit is 0, then we can write the Taylor series at 0, which is the Maclaurin series. And this is going to be, where is it? Yeah, here. Minus 1 to the n over 2n plus 1 factorial x to the 2n plus 1. So that converges for all x. So you see what we did? So Taylor polynomial says, if you have this one, so Taylor polynomial says, let me remind you what Taylor polynomial, Taylor's theorem say. Taylor's theorem says, just a reminder, that if the lim as n goes to infinity of Rn of x equals 0, then f of x equal to n equals 0 to infinity fn of a over n factorial x minus a to the n converges for all x. I need you to understand. Now all of a sudden I went to infinity. This is not the polynomial. So basically what this is, you continue, this is the Pn of x. This is the polynomial plus the remainder. Okay? So this is what it is. All right, I'm going to stop here and I give you some homework problems. Now there's some examples in the book. It's going to be page 647, number 1. I'm not going to give you too many. 10, 13, 15, and 27. Please look at, go over the notes and so forth. Have a happy Palm Sunday.